Have you ever wondered what existed before stars painted the night sky, before planets formed, and before the air you breathe came to be? In the beginning, there was only energy. The universe was young then, hot, dense, but silent. There were no atoms yet, no elements, no shapes to speak of. But inside this silence, something waited to form. Tonight, we drift through the earliest chemistry, through the cooling breath of space, and witness how the universe made its first elements. Imagine a place without substance, without matter as we know it, a glowing, formless sea of particles and energy. This was our universe in its infancy. Not empty, but not yet filled with the building blocks that would eventually construct everything we see today. The story of elements is the story of us, of stars, of planets, of life itself. It begins not with complexity, but with remarkable simplicity. In those first moments, the universe was a cauldron too hot for anything we would recognize to exist. No molecules, no atoms, not even their parts could stay together for long. Just raw energy and fundamental particles racing through an expanding space. But as this cosmic soup began to cool, structure emerged. The universe took its first breath, and in that exhalation, the most basic forms of matter began to appear. The elements that would eventually form the stars, the planets, the oceans, and even your body began as nothing more than potential, a whisper of what was to come. Think of it as the universe learning to write its own story. First, it needed to create an alphabet. The elements would be its letters, and with these letters, the cosmos would eventually write the poetry of existence. What we're about to explore is not just ancient history, it is your history. The origin of every atom that makes you who you are. Every breath you take contains atoms forged in these earliest moments. As you drift towards sleep, imagine yourself floating back through time, past civilizations, past the formation of Earth, past the birth of our Sunday, back to when the universe was learning to create itself. This is where our story begins, in the glow of creation itself, where light would cool into matter, where simplicity would become complexity, where the universe would make its first elements. Before we had soil beneath our feet, before oceans flowed, before clouds gathered in skies, the universe existed in a state we can barely comprehend. It was a symphony without instruments, a canvas without paint, a story without words. Scientists call this earliest era the Planck epoch, a time so brief and so long ago that it stretches the boundaries of our understanding. For the first fraction of a second after the Big Bang, the four fundamental forces of nature, forces that would later shape everything from atoms to galaxies, existed as one unified force. As you close your eyes, picture this moment of pure potential. A universe so compressed, so dense, that all the matter and energy we see today, all the stars and galaxies stretched across billions of light years, once fit within a space smaller than an atom. The temperature at this moment defies imagination, reaching values we cannot truly comprehend, billions upon billions of degrees. In this intense heat, not even the most fundamental particles could form. There was only energy rippling through the fabric of an expanding space. But the universe was breathing. With each cosmic heartbeat, it expanded. And as it expanded, it cooled. This cooling was the first alchemy, the first transformation that would eventually lead to the elements. As temperatures fell, the fundamental forces began to separate from one another. Gravity broke away first, becoming the force that would eventually shape the largest structures in the cosmos. Then, the strong nuclear force separated, the force that would later bind protons and neutrons together in atomic nuclei. This was the universe finding its voice, creating the rules and forces that would govern everything to come. Time itself was different then. What we now measure in billions of years passed in fractions of seconds in the infant universe. Creation unfolded at a pace we can scarcely imagine. In the gentle darkness of night, as you prepare for sleep, consider this strange beginning. Before there were elements, before there was chemistry as we know it, there was this dance of energy and forces, laying the foundation for everything that would follow. The elements we'll explore together, the hydrogen and helium that would become the building blocks of stars, the carbon that would one day form the basis of life, all of these were still just possibilities, waiting in the wings of creation. Our journey begins here, in this formless potential. In the next chapter, we'll witness the first 3 minutes of our universe, when the simplest nuclei formed, when the chemistry of the cosmos took its first tentative steps. For now, breathe deeply. Feel the connection between your body and this ancient beginning. Every atom within you has a history that traces back to these earliest moments. You are not separate from this cosmic story. You are its continuation. As our journey draws to a close, we return to the present moment with new eyes. The universe continues its expansion, stars continue to forge elements in their cores, and you, a collection of atoms with consciousness, continue to exist within this grand cosmic story. The elements that were created in the beginning still echo through time. Hydrogen atoms, born in the first 3 minutes after the Big Bang, still make up most of the normal matter in the universe. They float through interstellar space, gather in giant molecular clouds, fuel the fires of stars, and combine with oxygen to form the water essential to life on Earth. Some of these primordial hydrogen atoms are inside you right now. When you drink water, you consume hydrogen that has existed since the universe was just minutes old. These atoms have remained unchanged for over 13 billion years, witnesses to the entire history of the cosmos. Helium, too, carries the memory of creation. The helium that fills party balloons and makes voices sound high-pitched was largely created in those same first 3 minutes. Some of it was made later in stars, but much of it dates back to the beginning, unchanged since the universe was young. The heavier elements tell different stories. Carbon atoms speak of stellar cores, where temperatures and pressures forced helium nuclei to fuse together. Oxygen whispers of massive stars that lived fast and died young. Iron carries the memory of stellar catastrophe, of stars that exhausted their fuel and collapsed before exploding as supernovae. These elements continue their journey through time. They cycle through stars, through interstellar space, through planets, through living things. Nothing is static. Nothing is permanent. Everything is in flux. Atoms constantly rearranging themselves into new forms, new structures, new possibilities. Even now, this cosmic alchemy continues. In our Sunday, hydrogen fuses into helium, releasing the energy that sustains life on Earth. In distant supernovae, heavier elements are being created and scattered into space. In the coldest regions of interstellar clouds, atoms combine to form molecules, the precursors to greater complexity. The universe never stopped building. It began with the simplest elements, hydrogen and helium, with a whisper of lithium. From these, through stellar processes extending over billions of years, it created all the other elements. From these elements, through chemistry, it created molecules of increasing complexity. From these molecules, through processes we are still working to understand, it created life. From simple life, through evolution, it created us. We are the current endpoint of this cosmic journey, from simplicity to complexity. In our bodies, elements that were created in different cosmic epochs come together in intricate arrangements. Our consciousness, our ability to understand this story, represents a new kind of complexity in the universe, one capable of looking back and reconstructing its own origins. There is a profound unity in this cosmic story. The forces that governed the formation of the first elements still operate today. The atoms created billions of years ago still exist, though in different arrangements. The process of complexification that began with the first helium nuclei continues today in the evolution of life, of culture, of technology. As you drift towards sleep, imagine the long journey of the atoms that currently compose your body. Some were created in the first moments after the Big Bang. Others were forged inside stars that no longer exist. They traveled through space for millions or billions of years before becoming part of our solar system, part of Earth, part of the air water, and food that eventually became part of you. These atoms will not stay with you forever. Through breathing, through shedding skin cells, through countless metabolic processes, you constantly exchange atoms with your environment. The carbon atoms in your body today will be in the soil, the air, other living things in the future. Your physical form is not permanent but fluid, a temporary arrangement of elements that are constantly being replaced. This impermanence connects you to everything around you. The carbon in your cells was once part of plants, animals, soil, air. The water in your body has cycled through oceans, clouds, rivers, glaciers. You are not separate from the world, but thoroughly embedded within it, participating in cycles of matter that have been ongoing for billions of years. And yet, within this impermanence, there is continuity. The elements themselves endure. The hydrogen atoms you drink today may have once been part of an ancient ocean, may have once fueled a star, may have once existed in the bodies of dinosaurs. They carry the memory of cosmic history within their unchanging structure. The universe has not finished creating. It continues to evolve, to develop new forms of complexity. Stars continue to forge elements. Chemistry continues to create new molecules. Life continues to evolve new forms. Consciousness continues to develop new ways of understanding. The story that began with the first elements continues to unfold. As night embraces you and sleep approaches, remember that you are not separate from this cosmic story. You are part of it. Your atoms once floated in the emptiness of space. They were part of stars and clouds and countless other things before becoming temporarily part of you. And they will continue their journey long after your brief moment of consciousness has passed. The universe never stopped building, but it began with just a few parts: hydrogen, helium, a whisper of lithium. From these, everything else followed. Sleep now, knowing that your atoms once floated in silence, and that even now, they remember. The universe is expanding now. Cooling with each passing moment, we have entered what cosmologists call the era of Big Bang nucleosynthesis. The name itself carries weight, a scientific term for something beautifully simple: the birth of nuclei, the beginning of structure. 1 second has passed since the beginning of everything. The temperature has fallen to roughly 10 billion degrees, still unimaginably hot, but cool enough for something remarkable to happen. Protons and neutrons, the building blocks of atomic nuclei, can now stay together without being torn apart by the intense heat. At this moment, the universe is a luminous plasma. Particles of light called photons bounce constantly off electrons, protons, and neutrons in a cosmic dance. Nothing can travel far without colliding with something else. The universe is opaque, filled with this glowing, formless sea. The clock ticks forward. 2 seconds. The temperature continues to fall. Protons and neutrons are beginning to find each other in the cosmic soup. When they collide under just the right conditions, they stick together. This is the first marriage of particles, the first union that will lead to elements. A proton meets a neutron. They bind together through the strong nuclear force, forming a nucleus of heavy hydrogen, what scientists call deuterium. This simple union is the first step in building the elements. But the universe is still a challenging place. Many of these newly formed deuterium nuclei are immediately destroyed by high-energy photons, torn apart by the still intense heat. Creation and destruction exist in a delicate balance. As the temperature continues to fall, more deuterium survives. And now something even more complex can form. When a deuterium nucleus captures another neutron, it becomes tritium, a heavier form of hydrogen. When it captures another proton, it becomes helium-3, an isotope of helium with 2 protons and 1 neutron. By the 3rd minute, the temperature has fallen enough that these helium-3 nuclei can capture another neutron, forming helium-4, the stable form of helium that will one day float in birthday balloons and make voices sound high-pitched. 2 protons, 2 neutrons, bound together in a stable embrace. This helium creation is happening throughout the expanding universe. In these 3 brief minutes, roughly 25% of all protons and neutrons are being fused into helium-4 nuclei. The rest remain as single protons, the nuclei of ordinary hydrogen. Time continues its steady march. The universe is approaching its third minute of existence. The alchemy slows as the temperature and density decrease further. But there is one more element that forms in trace amounts. When a helium-4 nucleus occasionally captures another proton or neutron, it can form lithium, the third element on the periodic table. The universe has now created three elements: hydrogen, the simplest and most abundant; helium, making up about a quarter of all matter; and lithium, present in just trace amounts, a whisper of what's possible. These 3 minutes have changed everything. Where once there was only energy and individual particles, now there is structure. The universe has written the first letters of its cosmic alphabet. What makes these first 3 minutes so extraordinary is not just what happened, but how quickly it happened. In the span of time it takes to brew a cup of tea, the universe created the foundation for everything that would follow. This was the first great transformation, the first alchemy that would eventually lead to stars, planets, and life itself. The process unfolds like a cosmic recipe. The ingredients are simple: protons and neutrons. The heat provides the energy needed for them to combine, and as the universe expands and cools, this recipe produces the first elements in precise proportions that will shape the cosmos for billions of years to come. Imagine standing inside this newborn universe. The light would be blinding, the heat overwhelming. Around you, protons and neutrons would be colliding, forming new nuclei. Some would survive, others would be torn apart. This creative destruction would happen billions upon billions of times each second, throughout the expanding volume of space. The universe at this stage is a cosmic forge, a crucible where the simplest form of matter is being hammered into something new. It is a time of becoming, of potential being realized. There is a certain poetry in this moment. The universe, not yet 3 minutes old, is already creating structure from chaos, form from formlessness. It is writing the first verses of a cosmic poem that will continue for billions of years. As the temperature falls below 1 billion degrees, the forging of elements begins to slow. The nuclear reactions that create deuterium, helium-3, helium-4, and traces of lithium become less frequent. The universe has expanded enough that particles no longer collide as often. But what has been accomplished in these 3 minutes is nothing short of miraculous. From the pure energy of the Big Bang, the universe has created the seeds of everything that will follow. Hydrogen will fuel the stars, helium will add to their mass, and both will eventually play crucial roles in the formation of planets. Time in these early moments flows differently than we experience it now. Each fraction of a second brings dramatic changes as temperatures fall and new possibilities emerge. The universe ages rapidly, transforming from a sea of energy to a place where matter can exist in stable forms. By the 4th minute, the universe has cooled enough that the era of nucleosynthesis effectively ends. The temperature and density have fallen too low for further fusion to occur naturally. But the legacy of these 3 minutes will echo through cosmic history. The ratio of hydrogen to helium, roughly 3:1, will determine the types of stars that form hundreds of millions of years later. The first stars will use this hydrogen as fuel, fusing it into helium and releasing the energy that makes them shine. Inside these stellar furnaces, the next phase of element creation will begin. Think of these 3 minutes as the universe sketching an outline. The basic forms are there, the most fundamental elements. Later, the details will be filled in, the colors added. But without this sketch, nothing else would be possible. As you drift deeper into relaxation, imagine those first 3 minutes, the universe expanding and cooling, protons and neutrons finding each other in the luminous plasma, the first nuclei forming, breaking apart, and forming again as the temperature drops. The delicate dance of creation begins here. 3 minutes may seem brief to us now. We measure our lives in decades, our history in centuries, the age of our planet in billions of years. But these 3 minutes contained a universe of change. The moment when formlessness began to find form, when the cosmos first wrote the chemistry that would one day lead to stars, to planets, to you. The echo of these 3 minutes resonates through time. Every hydrogen atom, in every water molecule, in your body, every helium atom, floating in our atmosphere. They are artifacts from this earliest epoch, unchanged since those first moments. When you drink a glass of water, you consume hydrogen created in the first 3 minutes of the universe. So as night draws you towards sleep, remember this: you are connected to the beginning. Your atoms hold the memory of creation. The universe wrote its first elements into existence during those 3 brief minutes. And those elements now form the foundation of everything we see, everything we are, and everything we might become. The universe now breathes, expanding into increasing vastness. The first 3 minutes have passed, leaving behind a cosmos dominated by hydrogen and helium with just traces of lithium. But why did creation stop there? Why did the universe make only these lightest elements during its fiery birth? To understand this pause in creation, we must consider a delicate cosmic balance. The universe faced a race between time, temperature, and density. As space expanded, it cooled rapidly. As it cooled, particles moved more slowly, making them less likely to collide with enough energy to overcome the forces that keep atomic nuclei apart. Think of the early universe as a potter with clay that hardens too quickly. The artist begins to shape a form, but before more complex structures can be sculpted, the material becomes too rigid to work with. Similarly, the universe had only a brief window to form elements before conditions changed too dramatically. Hydrogen is the simplest element, requiring just a single proton as its nucleus. Helium needs more, combining 2 protons and 2 neutrons. Lithium goes further, requiring 3 protons. But to create the next element, beryllium, 4 protons must combine in a specific way, and this proved too difficult in the rapidly cooling cosmos. The universe faced what scientists call the mass 5 gap. There is no stable nucleus with exactly 5 particles. Helium-3 with 3 particles is stable. Helium-4 with 4 is remarkably stable. But combinations of 5 particles, like lithium-5 or helium-5, decay almost instantly. This created a natural barrier, a missing rung on the ladder of element formation. To climb higher on the periodic table, nuclei needed to combine in more complex ways, adding multiple particles at once. But as the universe expanded, particles grew too distant from one another for these complex combinations to occur frequently enough. Imagine trying to build increasingly complex structures while your building blocks are being pulled farther apart each second. Eventually, it becomes impossible to bring enough pieces together at the same time. Another challenge was the binding energy of these early nuclei. For elements heavier than lithium to form, more energy is needed to overcome the electrical repulsion between positively charged protons. As the universe cooled below 1 billion degrees, there simply wasn't enough energy available for these reactions. What we witness in these early moments is a universe of incredible potential, but also of natural limitations. Like a musical instrument that can only play certain notes, the early universe could only create certain elements. The rest would have to wait. This limitation was actually crucial for the future development of the cosmos. Had the universe created all elements during these first minutes, the story of stars might have been very different. Without abundant hydrogen to serve as stellar fuel, stars might have burned too quickly or formed with different properties. The incomplete periodic table was not a failure of creation, but rather a necessary foundation. It was the universe saying, "I will begin with simplicity, and from this simplicity, complexity will emerge in time." For roughly 380,000 years, the universe would remain too hot for stable atoms to form. Nuclei and electrons would exist separately, unable to bond in the intense heat. This era, known as the Cosmic Dark Ages, was a time of waiting, of potential unrealized. There is profound elegance in this cosmic patience. The universe did not rush to create everything at once. Instead, it established fundamental building blocks and then allowed time and space for the next stages of creation. Consider the gap between lithium and carbon on the periodic table. Elements like beryllium, boron, and carbon, are essential for life as we know it, but they could not form in the early universe. Between atomic numbers 3 and 6 lies a gap that would remain unfilled for millions of years. This gap represents a promise, a space left intentionally blank to be filled later by stellar processes. It's as if the universe laid down a partial foundation, knowing that the structure it envisioned would take time to complete. The cooling and expansion of space created conditions where energy became less concentrated, where particles collided less frequently. By the time the universe was 4 minutes old, the temperature had fallen to roughly 900 million degrees. Still incredibly hot, but too cool for the nuclear fusion needed to create elements beyond lithium. What's remarkable about this story is that we can calculate with precision the amounts of each element that should have formed. When scientists measure the hydrogen and helium abundance in the oldest parts of our universe, they find exactly the proportions predicted by our understanding of those first 3 minutes. This cosmic abundance, roughly 75% hydrogen, 25% helium, and traces of lithium, became the recipe for everything that followed. It determined what kinds of stars could form, how long they would live, and what new elements they could create. The pause in element creation was not the end of the story, but merely an intermission. The universe was setting the stage for the next act, when stars would light up the darkness and forge new elements in their cores. There is something peaceful in this cosmic patience. The universe did not need to create everything at once. It could wait for the right conditions, the right moments, for each stage of its unfolding story. As you rest and listen, imagine the universe in this state of becoming, mostly hydrogen, with islands of helium, drifting through the expanding darkness. No stars yet, no planets, no complex chemistry, just simple elements, waiting for gravity to draw them together, for new kinds of creation to begin. This simplicity would prove to be the universe's greatest strength. From just hydrogen and helium, stars would eventually form. And in those stars, all the elements needed for planets, for oceans, for life would eventually be created. The gap in the periodic table between lithium and carbon represents a division of labor in cosmic creation. The Big Bang created the lightest elements, and stars would later create the rest. Like a relay race, the baton of creation was passed from the intense heat of the Big Bang to the long-burning fires of stars. This division seems almost intentional, as if the universe designed a perfect system for element creation. The Big Bang provided the raw materials, and stars became the cosmic factories that would transform these materials into everything else. When we look at the night sky, we are seeing the second phase of this creation story. Every star represents a place where hydrogen and helium, born in those first 3 minutes, are being transformed into heavier elements. The story of elements is one of increasing complexity over time. The universe begins with simplicity, with just a few letters in its cosmic alphabet. But from these few letters, it will eventually write the complex chemistry of life. As night deepens around you, as sleep approaches, consider the patience of the universe. For millions of years, it waited with just these simplest elements. No rush, no hurry. Just the slow, steady expansion of space, the gradual cooling of matter, and the gentle pull of gravity that would eventually bring hydrogen clouds together to form the first stars. In this patience, there is a lesson. Creation takes time. Complexity emerges gradually. And sometimes, the most important thing is not what is created, but what is left to be created later, when conditions are right. In the vast silence that followed the first 3 minutes, hydrogen and helium drifted through the expanding darkness. These two elements, so simple in structure, would become the foundation upon which the entire cosmic story would unfold. Like primary colors that can create an infinite palette, these elemental building blocks contained all the potential the universe would need. Hydrogen, the first element, consists of just one proton and one electron. Its simplicity is deceptive. Within this humble structure lies the fuel that will power stars for billions of years. Hydrogen makes up roughly 75% of all normal matter in the universe, a cosmic abundance that speaks to its fundamental role in creation. Think of hydrogen as the universe's primary brushstroke, painting broad swaths across the cosmic canvas. It is the most versatile element, able to bond with nearly everything else to create countless compounds. Later, when planets form, hydrogen will combine with oxygen to create water, the solvent of life. It will join with carbon to form organic molecules, the chemistry of biology. But in these early days, hydrogen exists primarily as individual atoms, drifting through the expanding void. Its destiny is written in the physics of gravity. Over millions of years, these hydrogen atoms will gradually be drawn together, forming ever larger clouds. These clouds will slowly contract under their own weight, growing denser and hotter at their centers. Helium, the second element, tells a different story. With 2 protons, 2 neutrons, and 2 electrons, helium is more complex than hydrogen, but still remarkably simple. It makes up roughly 25% of all normal matter, the second most abundant element in the cosmos. Unlike hydrogen, helium rarely combines with other elements. It is noble, solitary, reluctant to form compounds. This chemical aloofness will later make it valuable for everything from deep-sea diving mixtures to cooling, superconducting magnets in medical imaging devices. But in the early universe, helium's role was more foundational. When gravity eventually pulls hydrogen together to form stars, helium will be there too. It will contribute to the star's mass, affecting how hot the core becomes, how fast nuclear fusion occurs, and ultimately, how long the star lives. Helium is both a product of stellar fusion and a participant in the life cycle of stars. There is a beautiful symmetry in the relationship between these two elements. Hydrogen fuses to become helium in stellar cores, releasing energy that makes stars shine. Later in a star's life, helium itself becomes fuel, fusing to form carbon and oxygen. The byproduct of one process becomes the input for the next, a cosmic recycling program of extraordinary elegance. The abundance ratio between hydrogen and helium, roughly 3:1, was determined in those first 3 minutes. This ratio would prove crucial for the universe's future. Had there been more helium and less hydrogen, stars would have formed differently, burned differently, lived different lifespans. The entire cosmic timeline might have been altered. Consider for a moment how remarkable it is that we can trace this ratio back to the precise conditions of the early universe. The temperature, density, and expansion rate during the first 3 minutes determined exactly how much hydrogen would remain and how much would fuse into helium. Had any of these parameters been slightly different, our cosmos might be unrecognizable. This hydrogen to helium ratio became the cosmic recipe, the proportions that would be used throughout the universe to build the first stars. Like a baker whose recipe calls for specific amounts of each ingredient, the universe used this ratio to bake its first stellar creations. For hundreds of millions of years, hydrogen and helium drifted through space, gradually forming larger and larger clouds. These clouds began to develop clumps, areas of slightly higher density. Each clump exerted a gravitational pull on the surrounding gas, drawing more hydrogen and helium toward it. As these clumps grew, they became more effective at pulling in additional material. A feedback loop developed where greater mass led to stronger gravity, which accumulated more mass, which further increased the gravitational pull. Slowly, inexorably, these clouds began to collapse inward. At the center of each collapsing cloud, pressure and temperature rose. Hydrogen atoms moved faster, colliding with greater energy. Eventually, in the densest regions, the conditions matched those of the early universe. Temperatures reached millions of degrees. Pressures became immense. And once again, hydrogen began to fuse into helium. But this time, something new happened. Rather than cooling through expansion as the early universe did, these dense cores trapped the energy released by fusion. They began to glow, to radiate light outward through the surrounding gas. The first stars were born. With the birth of stars, hydrogen and helium took on new roles. No longer just floating through space, they became the actors in a cosmic drama, playing out the physics of nuclear fusion on a stellar stage. Hydrogen became the primary fuel, helium the first byproduct, and later a fuel itself. Each star became a factory, converting hydrogen to helium in its core. The largest stars burned through their hydrogen quickly, living fast and dying young in spectacular explosions. Smaller stars, like our Sun, burned more slowly, converting hydrogen to helium at a measured pace that could last billions of years. The light from these first stars began to illuminate the cosmic darkness. For the first time since the release of the cosmic microwave background, the universe was filled with visible light. And this light came from the simplest of processes, the fusion of hydrogen into helium. There is something profoundly moving about this transformation. The same process that occurred in the first 3 minutes of cosmic history, the fusion of hydrogen into helium, now powers the stars. What was once a universe-wide phenomenon, happening everywhere at once, now occurs in concentrated pockets, in the hearts of countless stars, scattered through expanding space. Think of hydrogen as a cosmic storyteller, carrying the narrative of creation from the Big Bang to the present day. The hydrogen in the water you drink, in the cells of your body, was created in those first 3 minutes. It has existed since the beginning, unchanged in its essential nature. It has witnessed the entire history of the universe. Helium tells a different story. Some helium atoms were also created in those first 3 minutes. Others were forged later in the cores of stars. Yet despite their different origins, all helium atoms are identical. There is no way to tell whether a particular helium atom dates back to the Big Bang or was created in a star last year. In this indistinguishability lies one of the profound mysteries of quantum physics. The roles of hydrogen and helium extend beyond their abundance and their participation in stellar fusion. They also shape the large-scale structure of the universe. Their properties, particularly how they interact with light and gravity, influenced how matter clustered together over cosmic time. Hydrogen's ability to form molecular clouds, to cool through radiation, to collapse under gravity, all contributed to the formation of the cosmic web, the large-scale structure we observe today. Helium, with its different properties, played its own role in this cosmic architecture. As you drift towards sleep, imagine the choreography of these elements across cosmic time. Hydrogen and helium, dancing through the expanding universe, gradually drawn together by gravity, eventually igniting the stars that would illuminate the cosmos and forge all the heavier elements. Every atom in your body that is not hydrogen or helium was created inside a star. But without these first two elements, those stars could never have formed. Without hydrogen and helium, there would be no carbon, no oxygen, no iron, no gold. There would be no planets, no oceans, no life. The story of hydrogen and helium is, in many ways, the story of cosmic potential. From the simplest of beginnings, the universe created the conditions for unimaginable complexity. These two elements, born in the first moments, became the seeds from which everything else would grow. For 380,000 years after the Big Bang, the universe existed in a state unlike anything we experience today. Though nuclei had formed during those first 3 minutes, they could not yet capture electrons to become complete atoms. The universe was too hot, too energetic for these fragile bonds to survive. During this time, space was filled with a luminous plasma, a sea of charged particles. Electrons, with their negative charge, moved freely through this plasma. Nuclei, with their positive charge, did the same. And photons, particles of light, constantly bounced between them, like pinballs in a cosmic arcade. Every time a nucleus and electron would momentarily come together, attempting to form an atom, a high-energy photon would immediately break them apart. Creation and destruction happened in an endless cycle, with neither side gaining the upper hand. This constant interaction between matter and light had a profound consequence. Photons could not travel far before encountering a charged particle and being scattered in a new direction. The universe was opaque, not because it was dark, but because light could not flow freely through space. Imagine standing in this early universe. You would be surrounded by a brilliant glow, coming from everywhere at once. There would be no darkness, no shadows, no distinct sources of light. Just an all-encompassing radiance that prevented you from seeing any distance at all. But as the universe continued to expand, it continued to cool. And as it cooled, the average energy of those photons decreased. Slowly, the universe approached a crucial threshold, a temperature where atoms could finally form and survive. The exact temperature needed for this transformation was around 3,000 degrees. At this temperature, photons no longer carried enough energy to break apart newly formed atoms. For the first time, electrons could settle into stable orbits around nuclei. The simplest atoms formed first. Hydrogen, with just one proton and one electron, led the way. Like magnets finally allowed to come together, positively charged nuclei captured negatively charged electrons, forming neutral atoms. Helium followed shortly after. Its nucleus, with 2 protons and 2 neutrons, captured 2 electrons. These electrons arranged themselves in the first electron shell, the closest orbit to the nucleus, allowed by the laws of quantum mechanics. The trace amounts of lithium in the universe also formed complete atoms, capturing 3 electrons. But unlike hydrogen and helium, lithium stored these electrons in different arrangements, with 2 in the inner shell and 1 in an outer shell. This was the first glimpse of the electron shell structure that would later become crucial for understanding chemical bonding. Scientists call this moment recombination, though the name is somewhat misleading. Electrons and nuclei were not combining again, but rather combining for the first time. It might be better to think of it as the moment of first combination, the cosmic dawn of complete atoms. This transformation, from a plasma of charged particles to a gas of neutral atoms, happened throughout the universe in a relatively short span of cosmic time. Over the course of a few thousand years, nearly all free electrons were captured by nuclei. The consequences of this transformation were profound and immediate. Suddenly, photons, which had been constantly scattered by charged particles, could travel freely through space. With most electrons now bound to nuclei, forming neutral atoms, there were far fewer charged particles to impede the path of light. This liberation of light is known as decoupling. Matter and energy, which had been tightly coupled through constant interaction, now went their separate ways. Matter, in the form of neutral atoms, began to follow the pull of gravity more readily. Light, in the form of photons, began to stream freely through the expanding universe. These freed photons form what we now call the cosmic microwave background, or CMB. This is the oldest light in the universe. Photons that have been traveling unimpeded for over 13 billion years. When they were released, they were visible light, glowing red-hot like embers. But as the universe expanded, their wavelengths stretched, shifting them first to infrared and eventually to microwave frequencies. Today, we can detect this ancient light with sensitive instruments. It comes to us from all directions, a faint glow that fills the entire sky. This glow is remarkably uniform, varying by only tiny amounts from one direction to another. These slight variations, however, tell us about the small density differences that would eventually grow into galaxies and galaxy clusters. The moment of recombination marked a fundamental change in the universe. Before this time, the cosmos was opaque, a glowing plasma where light and matter were constantly interacting. After recombination, the universe became transparent. Light could travel freely across vast distances. The cosmic dark ages began. These dark ages were not completely dark, of course. The CMB photons still filled space, though they were quickly redshifting to longer wavelengths as the universe expanded. But there were no stars yet, no galaxies, no concentrated sources of new light, just vast clouds of hydrogen and helium atoms, gradually being drawn together by gravity. The formation of the first atoms was thus both an ending and a beginning. It marked the end of the early hot, opaque phase of cosmic history. And it marked the beginning of the era when structure could form, when gravity could begin to draw matter together without the opposing pressure of trapped radiation. This transformation was also the beginning of chemistry. With stable atoms now existing, the stage was set for these atoms to eventually form molecules. It would take time, certainly. The first molecules would not appear in significant numbers for millions of years, but the foundation was laid. Hydrogen atoms could now combine to form molecular hydrogen, 2 hydrogen atoms sharing their electrons. Hydrogen and helium could not form molecules together due to helium's closed electron shell, and chemical inertness. But hydrogen, with its single electron and partially filled shell, was ready to participate in chemical bonding. What makes this era so fascinating is that it represents a transition from a physics-dominated universe to one where chemistry became possible. Before recombination, the behavior of matter was governed almost entirely by the physics of charged particles interacting with radiation and with each other. After recombination, the stage was set for the chemical interactions that would eventually lead to the rich molecular complexity we see today. The universe at this moment was also remarkably simple compared to our current cosmos. It consisted almost entirely of hydrogen and helium atoms, spread thinly through expanding space. There were no stars, no planets, no complex elements, just these primordial atoms and the ever-fading glow of the CMB. Yet within this simplicity lay all the potential for what would follow. The slight variations in density left over from the very early universe were now free to grow under the influence of gravity. In regions where matter was slightly more concentrated, the gravitational pull was slightly stronger, drawing in more matter from the surroundings. Over millions of years, these overdense regions would grow, eventually becoming the seeds of the first stars and galaxies. The neutral hydrogen and helium atoms, no longer held apart by the pressure of trapped radiation, could now fall together more readily, beginning the long process that would eventually lead to the formation of the first stars. As you rest and contemplate this transition, this moment when atoms first formed and light was set free, consider how fundamental this change was for the future of the cosmos. Without stable atoms, there could be no molecules, no chemistry, no life. Without the release of the CMB photons, there would be no way for us to look back and see the conditions of the early universe. In a sense, the universe became knowable at this moment. By releasing the CMB photons, it created a fossil record of its early conditions, a snapshot of the cosmos when it was just 380,000 years old. These ancient photons, which we can still detect today, give us a window into the conditions that prevailed during this crucial transition. The story of the first atoms is a story of thresholds crossed, of new possibilities emerging from changing conditions. As the universe cooled below a critical temperature, electrons could stay bound to nuclei. As electrons became bound, photons could travel freely. As photons traveled freely, matter could fall together under gravity without the opposing pressure of trapped radiation. Each change opened the door to the next, in a beautiful sequence that would eventually lead to stars, planets, and life itself. The formation of the first atoms was not the end of a process, but rather the beginning of the next great cosmic chapter. So as you drift towards sleep, imagine the moment when the universe first became transparent, when light, which had been trapped in a constant dance with charged particles, was suddenly free to stream across space. When the cosmos transitioned from a glowing, opaque plasma to a transparent gas of neutral atoms. This was the moment when the universe first revealed itself, setting the stage for all the wonders that would follow. The universe now enters a period of waiting. For nearly 100 million years after the formation of the first atoms, darkness reigns. The cosmic microwave background photons continue to redshift to longer wavelengths as space expands. The hydrogen and helium atoms drift through the void, gradually gathering into ever larger clouds under the gentle pull of gravity. This cosmic patience is about to be rewarded. Within those growing clouds of primordial gas, something new is taking shape. As gravity pulls hydrogen and helium atoms closer together, the density at the center of these clouds increases. With greater density comes higher pressure, and with higher pressure comes rising temperature. In the densest regions, where gravity has worked the longest, temperatures begin to approach 10 million degrees. At this critical threshold, something remarkable happens. Hydrogen nuclei, which have been moving faster and faster as the temperature rises, begin to overcome their natural electrical repulsion. They collide with enough energy to trigger nuclear fusion. And so, roughly 100 million years after the Big Bang, the first stars ignite. These are not like the stars we see today. They are giants, containing hundreds or even thousands of times the mass of our Sunday. They are composed only of hydrogen and helium, with no trace of heavier elements. and they burn hot and bright, their enormous gravity crushing their cores to extreme temperatures. Within these stellar furnaces, hydrogen fuses into helium, just as it did during the first 3 minutes after the Big Bang. But this time, the process doesn't stop with helium. As these massive first stars burn through their hydrogen fuel, their cores become increasingly rich in helium. Eventually, the hydrogen in the core is exhausted, and the star contracts further, raising the temperature even higher. At roughly 100 million degrees, helium nuclei begin to fuse. 3 helium nuclei can combine to form carbon, an element with 6 protons. 2 helium nuclei can fuse to form beryllium, which can then capture another helium to become carbon. Through these processes, the universe creates its first complex elements, bridging the gap between lithium and carbon. Carbon marks a critical threshold. With 6 protons, it has a complex electron structure that allows it to form bonds in multiple directions. This versatility will later make it the foundation of organic chemistry, the chemistry of life. But for now, it exists only in the hearts of these first stars, a new creation forged in stellar fire. The process continues as these massive stars evolve. Carbon can capture another helium nucleus to form oxygen. Oxygen can capture helium to form neon. Neon becomes magnesium, which becomes silicon, which becomes sulfur. Step by step, fusion creates heavier elements, each the product of stellar evolution. This process can continue naturally up to iron, an element with 26 protons. Iron represents another threshold. It has the most stable nucleus of any element, the lowest energy state. Fusing iron does not release energy, but requires it. When a star's core becomes predominantly iron, fusion no longer provides the outward pressure needed to resist gravity. The star has reached the end of its life. For the most massive first stars, this end comes dramatically and quickly. Having lived for perhaps only a few million years, a mere eye blink in cosmic time, these giants exhaust their fuel and collapse. The collapse is catastrophic, releasing enormous energy that blows the outer layers of the star outward in a supernova explosion. These first supernovae are cosmic forges of unimaginable power. In the intense heat and pressure of the explosion, nuclear reactions occur that can create elements heavier than iron. Gold, silver, platinum, uranium, all the heaviest elements are born in these cataclysmic events, forged in the final moments of a dying star. As the debris from these explosions expands outward, it enriches the surrounding gas clouds with these newly created elements. The next generation of stars will form from gas that contains not just hydrogen and helium, but traces of carbon, oxygen, iron, and all the elements created by the first stars. This cosmic enrichment changes everything. The second generation of stars forms from gas that contains these heavy elements, incorporating them into their structure. Some of these elements form dust grains, tiny solid particles that can absorb and radiate heat more efficiently than gas alone. This changes how clouds collapse to form stars, allowing smaller, longer-lived stars, like our Sun to form. With each generation of stars, this process continues. Stars live, create new elements through fusion, die, and disperse these elements into space. The next generation of stars incorporates these heavy elements, creating even more during their lifetimes. Gradually, over billions of years, the universe becomes enriched with the full spectrum of elements we see today. Think of the periodic table as a record of cosmic history. The lightest elements, hydrogen and helium, primarily date back to the Big Bang itself. Elements like carbon, oxygen, and iron were forged in the cores of stars. The heaviest elements were created in supernova explosions or neutron star mergers. Each element tells a story of where and how it was created. Our Sun, a third-generation star, contains all these elements in trace amounts. When the solar system formed roughly 4.5 billion years ago, these elements were incorporated into the planets, including Earth. The iron in your blood, the calcium in your bones, the carbon in your cells, all were created inside stars that lived and died before our Sun was born. This story of stellar element creation reveals something profound about our connection to the cosmos. We are, quite literally, made of stardust. The atoms in our bodies were forged in stellar furnaces, cast into space by ancient supernovae, incorporated into our solar system, and eventually into us. We are the universe becoming conscious of itself, matter that has been transformed through cosmic history into living beings capable of understanding that history. The process of stellar nucleosynthesis, the creation of elements in stars, continues today throughout the universe. Even now, countless stars are fusing hydrogen into helium, helium into carbon, and so on up the periodic table. Every second, tons of new elements are being created in stars across the cosmos. Our Sunday participates in this process, fusing roughly 600 million tons of hydrogen into helium each second. This fusion powers the light and heat that sustains life on Earth. In roughly 5 billion years, when our Sunday exhausts the hydrogen in its core, it will expand into a red giant and begin fusing helium into carbon, briefly joining the ranks of stars, creating heavier elements. What's remarkable about this story is that it follows naturally from the physics of nuclear fusion and stellar evolution. The universe did not need special conditions or interventions to create the diversity of elements we see today. It only needed time, gravity, and the laws of physics. From these simple ingredients, cosmic evolution produced the entire periodic table. There is a beautiful progression in this story. The Big Bang created hydrogen and helium. Stars created elements up to iron. Supernovae and neutron star mergers created the heaviest elements. Each phase built upon what came before, adding new entries to the cosmic cookbook. The universe has now developed a cycle of element creation and recycling. Elements are created in stars, dispersed by stellar winds and supernovae, incorporated into new stars and planets, and eventually recycled back into the interstellar medium. Nothing is wasted, nothing is lost. The atoms in your body have likely been part of numerous stars, planets, and perhaps even living beings, before becoming part of you. As you rest and contemplate this cosmic alchemy, consider that you are not separate from this process. You are part of it. The elements in your body connect you directly to the stars. You are made of the same carbon that powers stellar fusion, the same oxygen that fuels fire, the same iron that makes up the Earth's core. You are, in a very real sense, a child of the stars. The story of elements is the story of increasing complexity. From the simplicity of hydrogen, with one proton and one electron, the universe has created elements with dozens of protons, neutrons, and electrons, arranged in complex structures. And from these elements, through chemistry, it has created molecules of astonishing diversity and functionality. The creation of elements was a necessary step for the universe to develop complexity. Without carbon, oxygen, nitrogen, phosphorus, and sulfur, life as we know it could not exist. Without iron, silicon, and aluminum, the Earth as we know it could not exist. The diversity of elements enabled the diversity of structures, compounds, and eventually, living beings that populate our world. So as night deepens and sleep approaches, remember that you carry within you the legacy of stellar fire. The atoms in your body were forged in the hearts of stars that lived and died long before our Sunday was born. You are connected, through these atoms, to the cosmic history we've been exploring. You are not just in the universe, you are of the universe. Made from its elements, governed by its laws, part of its ongoing story. There is something profound in knowing where you come from, in understanding your origins. As humans, we have always sought to trace our ancestry, to know our roots. Now, through science, we can trace those roots not just to our grandparents or to ancient human ancestors, but to the stars themselves, and beyond them, to the beginning of the universe. Every atom in your body has a history that stretches back to the first moments after the Big Bang. The hydrogen in the water you drink was created in those first 3 minutes. The carbon in your cells was forged inside ancient stars that exploded billions of years ago. The iron in your blood was created in stellar furnaces that no longer exist. When you look at your hand, you are seeing matter that has existed in countless forms throughout cosmic history. Those atoms have been part of stars, part of interstellar clouds, part of the solar nebula that formed our Sunday and planets. And now, part of you. They will outlive you, continuing their cosmic journey long after your brief moment of consciousness has passed. This atomic heritage connects you directly to the cosmos. You are not separate from the universe, observing it from the outside. You are the universe, a small but intricate arrangement of its matter, capable of contemplating its own existence. In you, the universe has evolved to the point where it can study itself, tell stories about its history, and wonder about its meaning. Consider your breath. As you inhale, you draw in oxygen created inside long-dead stars. As you exhale, you release carbon dioxide, sharing your carbon atoms with the atmosphere. With each breath, you participate in cycles of matter that connect you to all living things, to the oceans, to the rocks, to the air, and ultimately, to the stars. When you drink a glass of water, you consume hydrogen atoms that have existed since the first 3 minutes of cosmic history. These atoms have likely been part of countless water molecules throughout Earth's history, perhaps flowing in ancient rivers, perhaps frozen in glaciers, perhaps floating as clouds, before briefly becoming part of you. The carbon in your body has an equally remarkable history. Created by nuclear fusion inside stars, these atoms may have been part of many different organic compounds before becoming part of the food you eat, and ultimately, part of your cells. The same carbon atoms that now form your DNA once formed the bodies of ancient organisms, perhaps dinosaurs, perhaps plants, perhaps the first single-celled life on Earth. What makes this connection so profound is that it is not metaphorical or spiritual, but literal and physical. You really are made of stardust. The atoms in your body were actually created inside stars that lived and died before our Sunday was born. This is not poetry, but physics, not mysticism, but material reality. This deep connection to cosmic history gives us a perspective that transcends our brief individual lives. We are temporary arrangements of ancient atoms, borrowing them for a short time before returning them to the cycles of matter that have been ongoing for billions of years. In this way, we are like waves on the ocean, distinct forms that arise briefly from and return to something much larger than ourselves. There is something comforting in this continuity. Though individual lives end, the matter that composes us continues its journey. The atoms in your body will eventually become part of other living things, part of the soil, part of the air. Nothing is truly lost, only transformed. In this sense, we are immortal, not as conscious beings, but as collections of atoms that will continue to exist in different forms forever. This elemental connection also gives us a new understanding of our relationship to other living things. The carbon in your body is no different from the carbon in a tree, a bird, or a bacterium. We are all made of the same elements, arranged in different patterns. Our atomic kinship with all life is absolute and undeniable. Even our connection to the Earth itself takes on new meaning when viewed through the lens of our elemental heritage. The iron in your blood is the same element that makes up much of Earth's core. The calcium in your bones is the same element found in limestone caves. The sodium and chlorine in your tears are the same elements that make seawater salty. You are, in a very real sense, made of the same stuff as the planet itself. This perspective changes how we might think about our place in nature. We are not separate from or above the natural world, but thoroughly embedded within it, made of the same elements, governed by the same physical laws. Our bodies are temporary borrowings from the Earth, which itself borrowed these elements from the cosmos. There is also something humbling about recognizing that the elements that make us special, that enable life, are actually quite rare in the universe. Hydrogen and helium, created in the Big Bang, make up roughly 98% of all atoms in the cosmos. All the other elements combined, the carbon, oxygen, nitrogen, and others that make life possible, account for just 2%. We are made of cosmic rarities, elements that had to be manufactured in stellar furnaces and scattered by supernovae before they could become part of planets, and eventually, part of us. Our very existence depends on billions of years of stellar evolution, on countless stars living and dying to enrich the universe with the elements of life. Consider too how the proportions of elements in your body differ from their cosmic abundance. Hydrogen, the most common element in the universe, makes up only about 10% of your body mass. Oxygen, which accounts for less than 1% of atoms in the cosmos, makes up 65% of your body. Your body is a highly specialized arrangement of elements, selected and organized by the processes of life, in ways that differ dramatically from their distribution in stars or interstellar space. Even the arrangement of these elements reflects cosmic history. The iron in your blood is at the center of hemoglobin molecules, just as iron tends to sink to the center of planets. The carbon in your body forms the backbone of organic molecules, just as carbon forms the structural framework of interstellar dust grains. The chemical properties that make elements useful to life evolved in stellar cores long before life existed to make use of them. This cosmic perspective also gives new meaning to our environmental concerns. When we pollute the air, water, and soil, we are not just damaging something external to us, but the very source of the elements that compose our bodies. The cycles of matter that sustain life depend on the proper functioning of Earth's systems. By disrupting these systems, we ultimately harm ourselves. There is a responsibility that comes with understanding our elemental heritage. We are not just passive recipients of cosmic gifts, but active participants in the ongoing cycles of matter. How we use resources, how we treat the environment, how we design our societies, all affect the future journeys of the atoms that currently compose us and everything around us. As you rest and reflect on these connections, notice the sensation of your body, the feeling of being a physical entity composed of elements created in stars. Feel the weight of your body, the result of gravity pulling on your atoms, the same force that causes stars to form and planets to orbit. Feel the warmth of your skin, energy ultimately derived from nuclear fusion in our sunday, the same process that created the carbon in your cells inside ancient stars. Understanding our elemental origins does not diminish the wonder of being human, rather, it enhances it. We are not just bodies that somehow exist separate from the cosmos. We are the cosmos, arranged in a pattern complex enough to contemplate itself. The same forces that formed stars and planets formed us. The same elements that compose distant galaxies compose our bodies. The same laws of physics that govern the largest scales of the universe govern the chemical reactions in our cells. This is why the story of the first elements matters to us. It is not just ancient history, but our history. Not just cosmic evolution, but our evolution. The hydrogen created in the Big Bang, the helium, carbon, and oxygen created in stars, all of these came together in just the right ways to enable your existence in this moment. As night deepens around you and sleep approaches, remember that you carry within you the legacy of cosmic creation. Your atoms were forged in the hearts of stars. They were scattered by ancient supernovae. They drifted through interstellar space, became part of our solar system, part of Earth, and now, briefly, part of you. Tomorrow, they will continue their journey, transformed by your brief stewardship of them. In this knowledge, there is both humility and grandeur. Humility in recognizing that we are temporary arrangements of ancient matter. Grandeur in understanding that we are the universe becoming conscious of itself, telling stories about its own origins, wondering about its own meaning. We are not just in the universe. We are, made from its elements, governed by its laws, part of its ongoing story.